Good morning and welcome to chat with our esteemed guest. It is my honor to introduce him today. Today you will have the opportunity to pose questions and listen to Professor Anton Zeilinger. Professor Anton Zeilinger is emeritus professor at the University of Vienna and a senior scientist at the Institute for Quantum Physics and Quantum Information of the Austrian Academy of Sciences. And he has written, amongst many books actually, some of which you will also be able to buy at the bookshop outside, if in case you haven't not yet stepped into the realm of quantum entanglement and quantum physics. His work has profoundly shaped the way we look at the world, and specifically quantum physics. His work is actually, his name is now in close proximity as well with somebody who has also been to Alpbach before, Erwin Schrödinger, who is also now resting in peace close to here. And for his work, he has received numerous recognitions. Of course, we do know that Professor Anton Zeilinger is Nobel Prize laureate and received the Nobel Prize in Physics amongst with his colleagues on his work on quantum entanglement. But he has also received numerous other recognitions, such as the inaugural Isaac Newton Medal of the Institute of Physics, but also the John Stuart Bell Prize, the Wolf Prize in Physics, etc., etc. And there's actually a longer list, even more online, that I read through. Next to his passion for physics, he's also a passionate sailor and has actually called his sailing boat apparently with the number 42. 42 is nothing less but the answer to the universe in all questions. Who in here knows what a towel is necessary for? 1, 2, okay. A towel is necessary for any hitchhiking through a galaxy, as the Hitchhiker's Guide to the Galaxy has shown us. Because if you do have a towel, then you for sure haven't forgotten any other things, because the towel is the first thing you might forget. And it actually also has many other practical uses. So join us on a hitchhiker's journey through the galaxy of quantum physics. Dear Professor Zeilinger, I would like to invite you onto the stage. You will later on have the opportunity to ask questions to Professor Zeilinger. For that, I think I will have a second microphone, but I will introduce the process later. First, I would like to give a very warm applause to Professor Zeilinger and invite you onto the stage. And if I may, I would love to start this conversation with... Yes.
Yeah. First ask to change the lights. These lights are much too bright. Here it is much too dark. I cannot see your faces.
Good point. So that we can have a conversation.
Auf Deutsch bitte die Technik, das große Licht zurückfahren und mehr Licht im Saal, sodass ich mit Ihnen kommunizieren kann. Weil so sehe ich Ihre Gesichter nicht.
If this is possible to have the... Yeah, okay, working on it. Perfect.
Und im Saal mehr bitte. Nur ein bisschen weniger geht, glaube ich, da. Und im Saal mehr. Noch mehr im Saal.
Let's see. Aha, yeah.
So
that's sehr gut, sehr gut.
Aus geht's.
All right. Okay.
Can you still see me?
Okay. All right. Dear Professor Zeilinger, I would love to ask you to maybe share a short introduction to how you believe your advancements also in quantum physics have changed our view of the world as we know it.
How much time do we have?
I think in total, we have 1 hour until 11, but maybe if you would like to have a...
Is there a clock? There's no clock, right?
There's here you see on the right and the left. Yeah, exactly. But maybe we can start with a 10-minute introduction or 15-minute if you would like.
Well, let me start maybe to set the stage. Yeah, what do you want? What do you want me to say? Well, maybe I should mention a little bit about how I came to be interested in physics and science. And this began already preschool. Hat schon, the Kindergarten gab es damals nicht, but wasn't necessary. I grew up on the countryside, so we were outdoors all the time. And I was, from as far as I can think back, I was always interested on how things work. Like I would like to put things apart, see how they work, but I never was interested to put them back again, because I knew already how it works. So putting them back again would be a waste of time, uninteresting. Not much you can learn from. So I'm not an engineer. Engineers, the exact opposite, right? And then I had the big opportunity to have a teacher in gymnasium who was totally excited by physics, and he was able to excite us. And I tell everyone, every teacher in any field, the most important thing is that you bring across your excitement about the field. It's most important. Identify the really good guys in your class. And then I studied at the University of Vienna, which at that time was not a very good university. So, but I had a big luck. I had a big luck that there was no fixed Studienplan. So you could do the PhD directly. There was no need to do a bachelor and a master's, which in my eyes should be abandoned. People should decide whether they want to do a bachelor or a master's or a PhD. And the course, they should learn a course. I did not have to do many courses. I did not have to collect many shiny, I just had to convince a professor to give me a topic for a PhD thesis. And that's it. And this is how it should be. So you come much younger to a field, and etc., etc. Then about quantum mechanics, and now we come to your question. The curriculum was completely free, so there was no fixed schedule what I had to do. As a result, I did not take a single hour, lecture, seminar, whatever you name, of quantum physics. 0. But then it came to the PhD, and there were 3 of us who realized that this quantum physics sounds really interesting, so we should learn it. And we actually went to the professor who examined our theory and told him, please emphasize quantum physics in your examination. So we are forced to learn it. And we learned it. And I don't know how many physicists are among you, but I was immediately fascinated by its immense mathematical beauty. It's extremely beautiful. What do we mean by beautiful in physics? We mean that with very few symbols, which actually look nice, you can explain a whole big slew of phenomena. When you go across the street down there, you see the grave of Schrödinger, Erwin Schrödinger, Nobel Prize winner from Austria. And the Schrödinger equation is written on his grave. It's easy to find it. But when you go to the church, it's when you look to the church, it's on the left-hand wall, about the middle of the thing, and it has the Schrödinger equation. And the Schrödinger equation has only about 6 or 7 symbols. It's fantastically beautiful. It explains superconductors, it explains solid state, it explains the laser, and so on and so on. All this is explained by it. So much for the beauty. And the second thing which I realized was, when I read the textbooks, they all said, yeah, but what it really means, we will come back later in the book, and they never came back to that. So it was not clear what it means for our view of the world, for our Weltanschauung. And there were big fights about that. Yeah, and then I thought, this is interesting, maybe I can work on that. I was very lucky to have grown up in Vienna, where in Vienna, as opposed, still to this day, as opposed to most other places in the world, there is a fundamental, genuine interest in fundamental philosophical issues, even in the sciences. That does not exist everywhere. I went to 2 seminars once a month on philosophy and physics. And that way you really learn to ask the right questions about the thing. So the question is, what is it all about? We have wonderful equations which work very well, on which you can build technology, etc. Like your mobile phone, there must be about a couple thousand applications of Schrödinger's equation. So what does it mean? Some people say it describes things like cats being alive and dead, Schrödinger's cat being alive and dead, which is obvious nonsense, but people say that. There are things about 2 objects being located at 2 places, etc., etc. Now, to make a big jump, my point of view is quantum physics is about information. Information about the situation which you observe, you do an experiment or you observe something. Information about which allows you to calculate for the future. And now it comes. Just think a little bit about it. You see me sitting here. Why do you think I'm sitting here? Because you have information which comes to your eyes and maybe also other senses. And from that information you construct the concept Anton Zeilinger sitting here. The important point now being, and now I've finished my answer to your question, the important point being, there is no way to talk or think or whatever about reality without information. Okay? Therefore, this is now the point where some of my physics colleagues say I'm turning crazy because I'm getting old. Therefore, we do not need the concept of reality. We only need the concept of information, of information being the way to decide the truth value of logical propositions. And if that is true, the structure of physics must follow from the structure of information. And this is now a field going on very intensely. I proposed this already 20 years ago. Now more and more young people get interested in these strange things. And maybe someday we have a new Einstein who explains us all that. Now, to make it short jump to reality, we did many experiments, mainly with small particles or with photons and so on, to show the strange behavior of quantum mechanics. All these experiments were just done out of philosophical curiosity, nothing else. And suddenly people had ideas that this can be used in a technology. This was a total, in the beginning, about 50 years ago when we started. There was maybe a dozen people in the world working on this. And nobody of us had any idea that this might be technically useful. And now you have an emerging field, quantum information, quantum computation, quantum communication, all these things, which are based on our early work, which completely surprises me. For myself, I'm only interested in the foundations. I'm not interested in practical applications, because this is the most interesting. And I want to spend the rest of my days doing interesting work. So, thank you for now.
All right. You will now have the opportunity to ask Professor Zeilinger questions, and I think the best way of going about this would be, if you have a question, simply get up and come to this place of the room, and in the meantime, if you don't ask the question, you can also take a seat when you're waiting. Is there already any first question in the audience?
Can I say one thing? There's a little book which just came out, which features me in a lecture hall, you know, a Pixie book. I don't know if you know that. It's a book. It's not written by me, but it was published by this Pixie publisher. It was the idea of our Minister of Science and Education, Polashek, and they will, and every child which starts school this year will get from the school one of these books. But if you want one, and if you give a question, you just, after asking the question, come up here, I put the box there, and you can take one. Okay?
Sounds like a great deal. I can take the box. All right, yeah, perfect. Yeah, I'll put it there, thank you. Yeah. All right, with this added incentive, feel free to also ask questions. Yeah, please come to the front.
Maybe you guys can line up so it's faster.
So if anyone else has a question, please already.
I think you can line up, and then it's faster to handle the situation.
Sorry, my voice is failing me a little bit, but I wanted to ask, how do you think I'm trying to do my PhD, and when person looks for like what to do now, I feel always like overwhelmed by so many like new papers, new ideas. I feel like I never can catch up. I never can like be on the top of like what is happening now, because there is like so much new information. So how to just like stick with the topic, and focus on something and be sure that, and like make sure that I'm not doing something which was already done.
Which field are you working on?
Computer science, or like AI.
Computer science.
Yeah.
I mean, everybody is different, but I think the main, there's a lot being published now, and it's increasing. The number of the storage amount in computers worldwide is increasing exponentially for science papers. So, which means that someday the amount of memory you have to use will increase faster than the speed of light. Which is no problem, because then there will be no information contained anymore. But to be more seriously, the important point is to focus. The goal, in my eyes, the goal of every young scientist should be, or not a goal, the final step should be that you are better in your small field than everybody else in the world. Because you know more about this small field, you have put more energy into it, and so on and so on. And I would like to quote Eric Kandel. I don't know who of you knows Eric Kandel. He was of Jewish descent. He lived in Vienna, and he had to emigrate when Hitler came to save his life. And he grew up in the United States, and he became a Nobel Prize winner. And he always say, when you do science, focus, focus, focus. And every problem, is interesting when you focus enough. And don't worry if somebody around you says that this is not interesting or whatever. Another point is to not be distracted by whatever is published around you. If the field you focus on is well focused, then there are not many papers also published. Okay, in the general field, yes, but you have to get some overview. But that's not very important. And the third point is you need people to talk to. Be it your supervisor, which could be the right person, but I'm open, could also not be the right person to talk to. Maybe some colleagues or whatever, where you can toss back and forth your ideas.
Thank you.
You can take a book here, or two if you want. Okay.
Hello, my name is Bertan Taşdemir, and at high school I had a professor who liked to quote you quite often.
Can you hold the microphone closer?
Yeah, sure, sorry. My name is Bertan Taşdemir, and...
I hear everything you are saying.
Okay, perfect. And at high school I had a professor in physics who liked to quote you quite often. That's how I get to know you. And I wanted to ask, why is 42 the answer to everything?
I didn't completely understand it.
Why is 42 the answer to everything? Wieso 42 die Antwort zu allem ist?
Yeah, the precise thing is 42 is the answer to the question of life, the universe, and everything, right? Well, this is because, what was the name? Adams, the guy who wrote the book, defined it. You know, in every science, you can explain things which are by other things, deeper and deeper. And at some level, you must arrive at something which you cannot explain anymore, some fundamental assumption, right? Like in Buddhism, one fundamental assumption is karma, that karma exists. And I had a discussion with the Dalai Lama, and we talked about it. And then I asked him, but let me ask you a question. How do you know that karma exists? And he was laughing. He said, that is a typical scientist question. So there is something unexplained. So my fun answer number one is, this is how Douglas Adams, how he defined it. You know, the story is that it was actually the Earth in that book was a big machinery which was built to exactly answer your question. In the book, big machinery. And just before the Earth as a machinery finished it, it blew up. So we don't know the answer. Some people say there have been many fun articles written about why 42 is the answer. One is that you can, I think it's somehow you can construct the word love out of it, out of 42, for example.
Thank you.
You can take a book if you want.
Thank you, Anton. Nice to see you again after the book talk yesterday.
Closer, closer,
okay.
Please.
May I ask you a question about superdeterminism again? Because yesterday you said you believe in free will, but in superdeterminism, they believe even though we cannot predict directly the measurement outcome, we can predict the probabilities of the measurement outcome. It's because there is some missing information attributed to missing variables. Attributed to hidden variables. So in your experimental work, do you think there is room for such hidden variables to exist? How do you rationalize that you believe in free will?
Okay. Well, maybe I should explain a little bit the context of your question. In quantum physics, we have probabilities. And we believe that these probabilities are irreducible. So it's not like, you know, when I take a die, einen Würfel, wenn ich einen Würfel nehme, when I take a die and I throw the die, it shows a number, say 6. And this number is considered to be completely random. But in principle, the laws of physics which determine the motion of the die, including how the Würfel interacts with the Oberfläche, with the surface and so on, they are completely known. So in principle, this is a deterministic behavior, and it's only our ignorance, unser Nichtwissen, which says that this is random. Now in quantum physics, we have situations where we also have random situations, and where we know and even can prove that the assumption of a hidden explanation, hidden cause, cannot be held up because it leads to contradictions to some experiments. Okay? And some people said maybe there are hidden variables which you don't know. Now, this is part of the story of my Nobel Prize, that we ruled out these things. All of us together over 40, 50 years, we ruled out all these possibilities, so I am convinced that the randomness will stay with us until the end of the universe. Okay? And I think the worldview is actually a nice one. Suppose our world were deterministic. No freedom, everything would be decided. I would not want to live in such a world. The world where you have real randomness is much more open. It's much more free. Now, why do I believe it? You asked, you said exactly. This is a fundamental thing where we have good arguments. If we would go beyond, it would have been, it would mean a complete reconstruction of physics. Okay, not within our present knowledge. There could be a solution. Now, why do I believe in free will? Because otherwise I wouldn't be here, right? I would just sit somewhere on the beach and relax, not do anything, not do any experiments. I really believe it makes sense to make decisions.
Well, thank you very much. Is it
you can take a book.
To ask another question or
no?
Okay.
You have to line up again for another question. For the second question, you have to line up again.
Can you hear me okay? Can you hear me?
I can hear you very well.
Great. So science and failure often go hand in hand. And even the greatest thinkers, the greatest minds often fail and make mistakes. But often, our mistakes can actually be our most valuable experiences in shaping us as scientists. Even Einstein, when he referred to his greatest blunder, the cosmological constant, turns out that is an integral part of modern cosmology through dark energy. I'm wondering if you could please share some of your failures, maybe in your career, and how those have shaped you and influenced you to become the scientist and thinker that you are now today. Thank you.
Yes, thank you for the question. Yes, everybody fails. Everybody fails from time to time. And as a person, we fail. As a scientist, we fail, and so on. But luckily, we don't fail always. Well, that's a good thing, right? That's very good. Now, Einstein said that his cosmological constants, which he introduced, which people say today explains the dark energy, the accelerating expansion of the universe. But that he didn't like it, and he thought this was a failure. Well, on that point, I think the final word is not out yet. It could very well be, you know, we have two big open questions in cosmology. There are many other interesting. The big ones are where the dark energy exists and where it comes from, how it makes the expansion of the universe go faster. And the other one is dark energy, hidden energy, which we cannot detect, which doesn't exist. Dark matter, which we cannot detect. Dark matter is simply found, very simple thing, when you look at the galaxy from the outside, you know, these beautiful galaxies. Then you can measure how far a star, which is, say, halfway up the galaxy or whatever, moves around the center of the galaxy. Now it turns out that the stars move much faster than I mean, the point is, the more massive the center is, the faster the star is to move, unless it will fall into the center, right? Now, the problem is that when we look at the stars, they move much faster than what we would calculate from the knowing mass. And people did scores of work how to add more mass, what kind of mass could be there, so to explain the speed. And there's no way to find it. With standard ways to investigate, nothing happens. They don't find it. So they call it dark matter. Dark matter. And just yesterday, I read the result of a new big experiment somewhere in America, deep down in the mine, where they didn't find it again. Now, my personal opinion is that we could come to a situation where neither dark matter nor dark energy exists. That would mean that we have to revise our concepts of space. Maybe the way we measure distances is not correct. Maybe the way we define velocities is not correct, and so on. And I hope that there lies a cue for future deep insights. Now, about my failures, yes, we did a couple of failures. The most expensive failure was that we studied entanglement for 2 particles and for 3 particles. And then we said, it should be much more interesting if we have 100 particles or 1,000. And we bought a very, very big laser. We sent a very big laser. The way you do entanglement is you take a little crystal, send a laser in, and the particle of light of the laser decays into 2 or 3 or whatever particles. So when you have a very powerful laser, then it can decay into many more. And that experiment cost a lot of money and did not result in anything. Why? Because the results were so complicated at that time that neither existed the theoretical, nor the conceptual, nor the technical tools to analyze the situation. So I went too far. So we had to go back, you know. And I took the laser, and the colleague in the chemistry department needed such a laser for studying some new chemical reactions. So we gave him the laser. He was happy, and we kind of started something else. So the point is, when you do science on the borderline, you don't know whether you will be successful or not. When on the borderline of what is technically possible, what one knows, and so on. So you must fail from time to time. If you don't fail, your goals have not been ambitious enough.
Thank you. Can I take 2?
You take a book. You can take 2 if you want, right?
Hi, thank you for your time. I have a question about the university system in general, and particularly in Austria. You came out very famous, obviously, of our university system, but a lot has changed from when you studied. So we go through our bachelor's, our master's, and only in the PhD we really focus on one specific topic. Do you feel this can really foster innovation and research, or is there anything that has to be changed in our current system?
It can foster innovation and research?
Yeah, exactly. in one specific field?
Well, if I would do something, I would cut the number of Scheine, you know.
Certificates.
Certificates, Scheine, you know, you have to go to this lecture, I would cut it to at least half, if not even this. I would cut it much, and I would leave much more freedom to students to define their own way and find if they find this interesting or that interesting or not. Much more freedom. And also I would give students much time. Like, you know, I spent one semester permanently playing chess in a coffee house and didn't do a single Schein, nothing. Well, I don't think that was a mistake. So the freedom should be there. The freedoms, like, you know, one of the most silly things is sometimes very, very good, very gifted young students come to me, and they go to a course or something which is not defined for them because they are only in the first year. But I tell them, you know, I give you a grade and whatever, but the university system doesn't accept it. Even the computers are programmed such that you cannot put this into the computer. Isn't that silly? Well, it's absolutely silly. Stupid. And you know, another thing I would change is I hate online applications and so on. So I simply don't do that. If there is no way that I can do it by a phone call, then I say thank you very much. It's much waste of time. Much waste of time.
Thank you very much. We have like 18 more minutes, so let's try to see. I'm not sure if everyone will get to ask a question, but let's try to make it a short back and forth.
18 more minutes we have. Yeah.
Right? Yeah.
18 more minutes.
Well, you've worked in the field for quite some time now, and I mean, you've seen projects fail and succeed. So my question would be, do you have any specific breakthroughs you're hoping to be achieved in the course over the next few years?
I forgot. You know, I'm getting old. I'm not hearing so well. So I put in my earphones now.
Okay.
Just a second.
Repeat the question.
You're right. I forgot to put it in. Now this is actually extreme technology. You can totally express what this kind of thing can do for you. So, and here we go. Okay, now it's better.
Better? Perfect. So you've worked in the field of quantum physics for quite some time now, and you've seen projects fail and succeed. And my question would be, what specific breakthrough are you hoping to be achieved in the course of the next few years?
I think for me, the two goals.
Maybe with the microphone? Yeah.
There are two goals. Experimentally, I want to work. I don't know whether I can achieve the goals. It depends on how long I'm allowed to live. Really, my age, one thinks about that, is to use information from the very beginning of the universe to choose the measurement parameters in our experiments. So with big telescopes and so on and so on. This is a very challenging experiment, and I might not be able to finish it, but I hope I can put enough motivation such that others do it and finish it. That's on the experimental side. On the theoretical side, my basic position is that the fundamental constituent of the universe is information. Okay? And you don't need the assumption of a reality for that. And information means logical statements. Is it raining now? Yes or no? Something like that. Okay? Logical statements. And if that is true, you can have the logical statements, you can arrange logical statements in a sequence. The smallest statement has so many letters, and has more, the next one has more letters. You can quantify that. You can have a hierarchy of logical statements. That implies a structure, and that has actually been used for those who know about it. That is used by Kurt Gödel, for example, to show the incompleteness of any logical system which has sufficient complexity. Now, my hope is that in the same way we can explain someday the structure of quantum physics, and therefore the structure of physical law. This is an open question. It's extremely ambitious. I might not be able to answer it, but I like it. Thank you.
Thank you again. This is a question related to the quasar experiment you mentioned yesterday. So just to confirm, when you mentioned the emission spectrum of two quasars have similar fluctuation patterns, it will indicate that quite some amount of particles on those two quasars are quantumly entangled at the early stages of the universe. Is that correct?
No, this is not what I said. Okay. The two quasars are used to trigger the measurements on two entangled particles on Earth.
Ah, okay.
So they are completely independent.
I see. Yeah. Okay. Then.
Okay.
Thank you for the clarification. And the question is, for example, as you said, in the experimental setting, we started to induce quantumly entangled two particles, and you start to add more. And I know in the laser cooling, people start with the very few particles and they start adding more. But I just wonder if you ever experience existential dread in a sense, as in that you feel that our human technology is still very limited, even if we devote lifetimes of research into a topic. Do you ever experience that? For example, if we build a telescope that is the size of the distance between the Earth and the Sun, but we will only be able to look a little bit further into space?
Well, in general, maybe you can pass on the mic now. In general, there are always limits which we can see, like how large a telescope you can build or whatever. All these limits, when people, they don't limit what you can do. With most instruments, we did much more things than was envisaged when we started the whole thing. Okay? So to me, these are not real limits. Okay? So how much time do we have now? 10 minutes or what?
I just heard that if you would be okay with that, we can actually go 10 minutes, 15 minutes over.
Well, actually, I should be. Maybe let me propose one thing. If it's okay, we finish the line with who is standing here now. Yeah, okay. And we let these people ask the questions, and please be brief, and I will also try to be brief.
Perfect. Okay. That sounds like a great proposition. Please.
Yeah. So I'm not a physics major, I'm more of a builder, but I'm more curious about the concept of quantum entanglement and how subatomic particles are interconnected. So, can you hear me?
Can you hold it closer to your mouth, please?
Okay.
Yes.
Is that good?
Yes.
Okay. Yeah. So, I'm more curious about the concept of quantum entanglement and how subatomic particles are interconnected. So when it comes to understanding how a black hole works, when we pass through the event horizon, are we going through time? And does that mean that the quantum entanglement work still exists in that period?
Well, the idea is that on the event horizon, You can have one of the entangled particle inside and the other one outside. And the one outside looks completely random to you. You don't know that it is entangled. So the information in, for example, a black hole would be entangled then with the information outside. But I don't have the foggiest idea how to prove that. But it's a good question, yeah? Thank you.
Hey, winning the Nobel Prize comes with a lot of attention and probably influence and maybe in some way power. Do you think one should use that attention, influence, power, maybe also politically to, well, achieve something for society, for example? So I'm a PhD in physics, and many physicists are not as interested as one might think in climate change and the climate crisis. So do you think one should maybe use the influence that you have to put the attention of politicians or societies like the Austrian Physical Society more towards climate change and solving this problem?
That's a very good question. Let me say one thing first. This is difficult. So the answer is yes, but how? In our society, I find it extremely complicated to discuss via the things, via the social networks or whatever, etc., etc. Because these systems have a tendency, for physics it's easy. They are nonlinear processes, so there's no way to see how where this leads. I have been invited by a couple of Austrian members of politics, ministers, and also other people, to talk to them personally and privately. So and these discussions are very, very interesting, very focused, and since they are not for the public, the poor politicians really mean poor. They don't have to watch every word they are saying because they might immediately be attacked. So this happens. I should not mention who I meet and what we talk about, but the spectrum is extremely broad. And I personally have in general a much more positive view of politicians in our country than what is communicated by the press in general, right? Now, about climate change, etc., this is a very interesting, scientifically, this is a very interesting topic. I mean, it appears that climate change happens. Even as some people say, of a climate change you can only talk about a decade or 2 decades of observation. I don't believe that, so it happens. But the question is, what is the cause? What is the cause? And there is some possibility, which is, I don't want to judge how big it is, that the cause is much more surprising and conceptually much deeper than human cause. There was an interesting article recently by, I don't remember the name, by the chief of meteorology and climate research at NASA, you know, the American Space Agency. And they observe the weather and climate on the Earth since the first satellites. So they have an immense amount of data. And he wrote that we analyzed what's going on since the early days, and since particularly then that gave them a lot of information to identify the last year or so. And he wrote, in the last year, the climate temperature increase was much larger than any model proposed. And, you know, and they calculated everything. They calculated the human influence, carbon dioxide, whatever. All models put together explain at most 10% of what's going on. From that, as a scientist, he says, I have to say that we don't have the foggiest idea what is really going on. For a scientist, this is very interesting. For humanity, we don't know yet because we don't know how it will go on. So I ask everyone. I mean, if somebody, whatever position somebody has in the climate side, I ask them, what would disprove your idea? As a scientist, you have to, you know, according to Popper, you have to. Any idea has to have the possibility to be falsified, right? Otherwise, it's not science. What would be for you the falsification of the statement that this is human-made? Or, on the other side, what be, since you are saying this is not human-made, what is for you the concept or the observation which would prove that you are wrong? And the answers are very, very, very weak. It's very, I mean, scientifically it's very interesting. Maybe we make an exception for a
No, just for clarification. So you would say that the climate crisis is not human-made? No.
I am saying the climate is here, but we don't have enough evidence to claim what the cause is.
Unexplained variant.
I'm not saying it is not human-made. I'm saying there's not enough evidence. Okay?
Thank you, Professor. I have a more philosophical question, or a theology question, whatever you want to deem it. Quantum physics is often used by theologians to prove the existence of God, or to argue for it. And if I remember correctly, in one of your interviews, you also mentioned the role of God in quantum physics. So my question would be, is there a role for religion or God in quantum physics in your work?
The answer is first no, but it's more complicated. A scientist can, in my eyes, as a scientist, can only be an agnostic, in the sense of saying that the role of God or whatever has no role whatsoever in your scientific approach, neither plus nor minus. So scientists can neither disprove the existence of God nor prove the existence of God. There have been many mistakes in the history where people overdid it, where people, you know, famous Galileo case or whatever, on both sides, or Dawkins who thinks that he can disprove the existence of God, which are, in my eyes, these are always special images of God which you can shoot down. Okay, so this is completely independent. The other, I mean, like I know a number of scientists who are atheists in the sense that they believe there's no. I know a number of scientists who believe in the existence of God. There is no contradiction. So this is open. But science can never, in my eyes, prove the existence of God. This is a completely different field. You want one of the books? No? For children in your family, or maybe two, or whatever.
Hello. I have a philosophical question as well, related to the interpretations of quantum mechanics. So, what is your view on different interpretations, like many worlds or Copenhagen interpretation, or some other?
I think, in my eyes, I am convinced that what the early guys said, like Bohr, Heisenberg, and so on, this is really these are the most fundamental statements about the interpretation. It's the Copenhagen interpretation, which has to be further developed. The Copenhagen interpretation already says, a famous statement by Bohr, there is no quantum world, there is only an abstract quantum theoretical description. The other interpretations, like many worlds or whatsoever, try to save one way or another the concept of classical reality. And this is not a way into the future.
Hello, Professor. I have a question. I'm from the University of Innsbruck, and I was there when you were honored at Innsbruck a year ago or so. And you said an interesting thing. You said that the high-performing students in each class of schools were not so much supported as they needed, like the less performing students. And I wanted to ask a very concrete question: how would you do that? So the high-performing students, foster them more.
We talk about high school, gymnasium. That's the situation, right? One way. I mean, the really high perform students in whatever field, they are by necessity, because this is a rare gift. They are a minority, and they are very often the only ones in their class. And there's a lot of social pressure on them. I experienced that myself. So what can you do about it? You can identify in the school these high performers and put them together. So they realize that they are not crazy, they're not the only ones, and they find others who they can talk to, and who can encourage each other. Right? Just quickly, yeah.
Just that. But would you do would you put them together all the time, or just say all Mondays or 1 hour or so?
No. They should stay in the normal class, because the social contact and so on is extremely important, etc., etc. They should meet, like maybe once a week, or could meet, but whenever they want, etc.
In the beginning, you were talking a lot about beauty in quantum physics, and that reminded me a lot of making music. So do you feel like this emotional approach to what you're doing is kind of the same as you would need in music? And does your making music help you with that? Or do you feel like quantum physics also could help musicians in like improving?
Well, there is a very interesting study in brain research. This was by a British brain researcher. His name is Zeki, Z-E-K-I, Zeki. He found out that he studied by how to call this, encephalography. He studied how much of your brain is activated when you do something. And he found out that people who are doing arts, be it music or some other arts, and who then themselves say, now I'm completely in it, I really do it, they have a very large part of your brain simultaneously activated. And the same for scientists. So there's an analog, there's an interesting analog. And for myself, I had a number of my ideas when I was doing music or listening to music. It's very interesting. It's not isolated activity. Neither of them is isolated.
What is your take on time irreversibility in quantum systems? And I would like to record the answer, if it's okay for you.
No, I don't want any answer to be recorded. I can give you the answer. The laws of physics of quantum physics are time symmetric. Okay? So in the same way, you can predict, when you observe a system, you can predict its future, or you can retrodict its past. And both of them are not perfect. Both of them have probabilities and all this. So in principles, the laws are time symmetric. And in quantum, you can go so far that you can teleport the state of a system back into the past. Okay? Under one condition. Under one condition, namely that you don't change the history.
All right, thank you, if you would like.
Okay.
All right, thank you everyone for your questions. Dear Professor Zeilinger, if you have any, would you like to add any last comments to this session to let the students go back? We are soon closing the Forum Alpbach, so they're soon gonna also head back to their home countries, their studies.
Oh, today you were closing?
Tonight is the closing party, yeah.
I mean, what I want to tell you in every field, including climate research or whatever, yeah? Believe your own mind. Believe when you look at the things, everything. Believe what you want, what you find interesting, and don't get distracted from that.
Right, yeah, beautiful last words. Thank you very much. Let's give a warm round of applause. And outside there is a bookstore, and don't forget, if you would like to get yourself a copy of The Dance of the Photons. A very nice introduction into quantum physics and the basis on which Professor Zeilinger got his Nobel Prize. Thank you.